In my excitement, I just tossed an object off my desk. So, welcome everybody to this, the first of two sessions about IPOS. So IPOS is the Institute for Photonics and Optical Science, and I'll tell you what photonics is in a minute. But the session on Wednesday is about nanophotonics, so photonics on the nano scale. Today we have three speakers, including myself, talking about photonics at small scales, but not quite the nano scale. All right, so let me explain to you what photonics is. And it's always mentioned together with optics. And the border between optics and photonics is somewhat blurry, but there's a couple of demarcations between the two. One of them is that in optics you consider light carrying energy, and in photonics you consider light carrying information. Perhaps a simpler one is that you call optics that is anything that doesn't use a laser, and you use photonics for everything that does use a laser. There are other definitions, but it's really the modern aspects of optics that is now referred to as photonics. And of course, the link here is that it is associated with, it is in analogy to electronics. Now, IPOS then is the umbrella organization for all the optics and photonics research at the University of Sydney. And so you'll hear today about the people in physics, but we have colleagues in chemistry and colleagues in electrical engineering working in the same general area, and they're all, and we interact with them through IPOS. Perhaps the first thing to say as a general introduction to optics and photonics is that light-based science, in my view, combines the best of two worlds. There's deep science, and today and Wednesday will illustrate that. And there's also there's an established industry, and there are established applications. And let me just talk about each of these very briefly before handing over to Simon and Maryanne. So the first one is that optics and photonics, though it is not perhaps as obvious as some other areas, is really considered to be one of the great enablers. And in fact, it was brought out in the last few days, last week in fact, when a report on the state of the optics and photonics industry in Australia and New Zealand was launched. And let me quote two things from it, just to give you an idea of where optics and photonics sit. So, light-enabled products affect every facet of modern life, and the value of these products has been recently reliably estimated at just over 10% of the world's economy. That is a large number, as you will agree, and is growing substantially faster, at a substantially faster rate than the average compound annual growth rate of manufactured products. So the message here is optics is huge, though it is not always obvious that it is. And let me give you an illustration of that. There's a number of examples in this report, but I thought the following one was quite interesting. So the smartphone's display is a photonic device and is produced using photonic systems for machining and assembling. The aluminium or glass case is machined using high power lasers, as are many of the circuit boards within the body of the phone. The high performance camera in the modern phone are marvels of photonic design, as are the face recognition systems used to unlock the latest generation. Even the silicon chips within the phone are patterned and machined using lasers. So again, it may not be obvious, but optics and photonics is everywhere. And I believe Simon has another few examples to illustrate this. In addition to that, as I mentioned earlier, optics and photonics also represent great deep science. And some of the work that's being done at IPOS, I've just written down here. There's optics at the nanoscale. So manipulation of light waves at scales that are much smaller than the wavelength. You may remember from your optics courses, that's really hard because there's a diffraction limit for light. Well, you can go below it if you use metals, for example. There's a large research effort by Ben Eggleton which has to do with the interaction of light and sound. And the trick there is that when the light wave and the sound wave have roughly the same wavelength, then, which is a condition which can be satisfied, then they interact strongly. And so you can put information from light waves onto sound waves and vice versa. There's nonlinear optics and solitons, which I will talk about in a minute. There's quantum optics, which Stefano does in some of his work. And there are novel types of lasers. And these are not just any lasers, but the lasers we're talking about here are submicron in size. They're really extremely tiny. They have very low thresholds, and they in principle can have very good output beams. So that is what I wanted to say as an introduction. I'll now give the floor to Professor Simon Fleming and Associate Professor Maryanne Large, who will talk about their research, and then we'll get back to me after that. So I'll stop share, Simon.
Thank you, Martijn. I will try and share my screen now. Okay, hopefully you can see that.
Yes, thank you.
Yes, I'm Simon Fleming, and what I wanted to tell you about is our work on novel wearables, technology for monitoring people's health and so forth, using a breakthrough technology of very low Young's modulus polymer optical fibres. Before getting into those details, what I thought I'd do was start a bit like Martijn, looking at the whole area from an overview. So, as Martijn said, photonics is one of these, is very big, and in some respects it's hidden. You don't really come across it so directly, but it enables a huge amount of economic activity. The number I had here was from a report about 4 or 5 years ago, which estimated that the global industry is about $10 trillion US that's enabled by photonics. You drill down into that to look at the direct value of that, selling of lasers, selling of optical fibers, selling of lenses and so forth, is about $500 billion globally. The interesting thing is that it's also an area of high tech that Australia and New Zealand are strong in. The direct economic value in our two countries is about $5 billion. And that's equivalent to the Australian dairy industry plus the New Zealand wine industries. Now, everyone knows that they're big, but it's quite a surprise to most people that there's that amount of photonic activity in these countries. There's about 12,000 jobs distributed over almost 600 companies. When you drill into the details there, many of those companies are really quite small. They're startups, high-tech startups. So it's a really exciting area of science with a strong take-up of in terms of manufacturing and commercialization. The fact that we've got all that economic activity happening is quite a strong research sector across a number of universities, especially the IPOS group at the University of Sydney. So I wanted to look first at optical fibre just broadly, because we're looking at a very specific type of fibre, but I thought it was just worth saying a little about fibres generally. They've transformed the world in terms of how they've been applied to telecommunications over the last few decades. Essentially, the entire world is wired up with fibre under the oceans, and it isn't just transoceanic cables. Fibre goes to the home in many cases and to the 4G wireless pole. So essentially any call that you make, whether it's a wireless phone call or whether it's a Zoom call, video call around the world, it's almost certainly being carried by optical fibre. And there's a huge technological advancement that's gone on here. If you look at the growth in capacity in fibres over the last, say, 25 years, you're looking at about a million-fold growth in capacity. So I think it's fair to say that fibres have transformed the world over the last few decades. So we have been active in that area for about that time, and have a fibre draw tower in the School of Physics. And this positions us to be able to do some really interesting experimental research. So the picture in the middle here is this experimental draw tower. It's a scaled down version of what's used in industry. It's well established. It's a microfabrication technique that can get to the borders of nanofabrication. And the key thing to know about it is you make a big macroscopic version of the fibre, put it in a furnace, and then draw it down into fibre. So this technology for telecommunications is well established, and what we've focused on is using it to do interesting research things. So for a decade or so, we've been focused on what are called microstructured polymer optical fibres. And a standard fibre that you'd use for telecommunications has a simple core inside a cladding. If you make a really complex transverse structure, you've got access to a lot of different mechanisms for guiding light, and you can control the way light is guided in very interesting ways. You can control the dispersion, the modal properties, what the light interacts with as it's propagating. So that opens a whole set of interesting research questions. So that's where we've focused for quite some time and have pretty much world expertise in drawing microstructured polymer optical fibres. However, what we've been drawing is fibres out of hard polymers, not quite as hard as glass, the fibres that are used in telecommunications, but still quite hard. And we started thinking, well, we wanted to explore how this technology could be used in health and medicine. And the particular area we're interested in was in wearables. And these fibres don't really lend themselves to being attached to clothes or the body. So we were thinking about what would we need for this? So we're interested in monitoring, physical properties of people. And the reason for doing that, there's a whole stack of reasons, but the aging population, the desire to have people healthy at home for longer, reducing the healthcare costs, improving the quality of life for people who are either old or unwell. So wearable sensors opens up a whole set of possibilities for monitoring people's health remotely. Now, the key thing to know about an optical fiber sensor for this application is you're measuring some mechanical aspect: pressure, strain, bend, twist. And there's really two important parameters. The first one is the Young's modulus, the stress over strain. If you're looking at measuring something mechanical, by perturbing the way the light travels down the fiber, you want to have a small amount of force causing a large amount of deformation to the fiber. So you want a low Young's modulus. On the other hand, there's an extent to which you can stretch a fiber or anything before it breaks. So the breaking strain is also important. So you want that to be high. So we started looking at polyurethane for making optical fibers. And the reason for this is the stiffness is about 3 to 5 orders of magnitude less than silica. So it will be much more sensitive. The breaking strain is about 500 times that of silica. So it would be much more rugged. The other reason for looking at polyurethane is it's already widely used. It's used in clothing. Lycra and spandex have polyurethane as part of them. So it isn't a large stretch to think that you can make wearable devices in polyurethane optical fibers. The other thing is, if you're unfortunate to go into hospital and be intubated, those tubes are typically a version of polyurethane. So it looks like we're starting from the right material, both from its mechanical and optical properties and from its compatibility properties. So we set about drawing fibers, and this gives a little sort of rogues gallery of some of the exotic structures that we've made. And that persuaded us that we had sufficient control over the fabrication technique to be able to make fibers that could be useful. So we then made the next step of trying this out. This is one of the postdocs, and we strapped an elastic bandage around him, put one of these fibers on it, launched a laser into it, had a detector, and got him to breathe. And we get a really good signal there for exhalation and inhalation. So, wow, we can see him breathing. So we thought we'd make him work a bit harder and put him on a treadmill. And that's him running at 2 kilometers an hour. That's him running at 7 kilometers an hour and 11 kilometers an hour. And you can see a couple of things going on there. So we did some frequency analysis on that. And what we find is a number of peaks. And the first one corresponds to his breathing. We were perfectly able to get his breathing. The surprising thing was we could also get his footfalls, his steps as he was running. So it turned out to be very sensitive, a lot more sensitive than we were expecting, especially for such a crude demonstration. So having persuaded ourselves that this worked, we thought, let's look at solving a much more significant problem, and that's blood pressure monitoring. Well, it's pretty easy to get your blood pressure measured. You get one of those pump-up cuffs that you probably had at the doctor's, and that will give you your systolic and diastolic blood pressure. But if, say, you've had a heart attack and you need to be monitored continuously, then it's a real problem because those cuff systems are not at all suitable for that. You don't want to be woken up every half an hour through the night by this thing pumping up. So there's a real need for an affordable, continuous, unobtrusive way of measuring blood pressure. So we thought we'd explore using these fibers for that. And the basic idea is shown in this diagram: blood flowing on that red line through an artery, place 2 of these extremely sensitive optical fibers across it, and use them to pick up the signal of the blood pulsing underneath. And we found that we could do that pretty reliably. And by looking at timing differences between the known distance between the fibers, you can get the blood pressure. So that was done on the bench. We then did an extremely crude experiment where we got 2 of these and just stuck them on someone's wrist. And again, we can get usable signals out. And the signals look about right for extracting some of the important information about the state of the heart. So that's really where we are at the moment with this. It's an exciting new technology with quite a few potential applications. We've focused on blood pressure, and it's work that's in progress at the moment. So in terms of sort of wrapping up what I wanted to say, we've got this really interesting new technology in polyurethane optical fibers. The initial demonstrations are really promising. It's got extraordinary mechanical properties compared to standard optical fibers. We're currently looking at blood pressure. There's several opportunities to get involved in this around enhanced fiber designs for the current application, refining the performance in terms of the hardware and software for extracting information about it. And whilst we've focused on this because we think it's an important problem, there's all sorts of other problems that are likely to be accessible by this approach. Fetal heartbeat. There's a lot of interest at the moment, for obvious reasons, in being able to listen to people's chests, to understand respiratory problems, bedridden patients, making sure that they're turning and measuring their heartbeat. And outside of healthcare, there's sports performance monitoring as well is a possible application. So that wraps up what I wanted to say. Martijn, do I pass over to Maryanne directly?
Yes, please.
Okay.
Okay, hi everyone. So I'm slightly here under false pretenses because although I am genuinely a photonics person, the particular application that I'm going to be talking about today isn't really a photonic application, but it is based on the fiber draw process that Simon described. So basically, Simon sort of described a trajectory of going from sort of telecommunications to being able to make these weird structures and being able to make weird structures in weird materials, and moving from the sort of very predictable applications of optical fibers in telecommunications and engineering to biomedical sciences. But at the point where we had this polyurethane material, which Simon didn't mention, is actually a really poor optical material. We started thinking about what can we do with this ability to make essentially highly tailorizable, funny, very long structures. And so we started to look at an application which uses those and is pretty unusual. And it's basically to use them as flexible bioscaffolds for regenerative medicine. So what is regenerative medicine, and what are we sort of looking to do this? Well, when I was a kid, there was a very famous sci-fi TV series called The $6 Million Man, and it had this opening sequence in which Steve Austin, who's an astronaut, and you can see that with the sort of phallic symbolism in the back of the in the back of the picture of season 2, he has this crash, and they have to rebuild him. And so obviously $6 million was an awful lot of money in 1973. But they had this process by which they could rebuild him and rebuild him better. They had to give him a new arm and so on. And that, you know, for most of my life has really been science fiction. But it turns out that that is now becoming a reality in particular boutique areas. And one of the things that's enabled this with all of these technologies, the technologies are combinations of technologies. So in our case, there's technology around the materials, there's technology around the fibre processing. And then, of course, there's the technology around the biology. And the extraordinary thing, which really does seem like magic to me, is that you can take cells from a patient. If you take the stem cells from a patient, they're cells that, if you put them in the right environment, they can differentiate into all the kinds of cells that we have in the body, which is pretty amazing. So literally, you can take a sample of somebody's cells and you can grow liver cells or muscle cells or bone cells. And so what's required to do that is the right mechanical and biochemical environment. And so that it turns out that within the school, we've got a combination of some pretty unusual capabilities. One is, as Simon mentioned, this ability to make these incredibly soft, biocompatible fibres. We're also able to make them with funny structures and funny surface structures. And working with Marcella Bilek's group in the plasma group, we're actually able to use a plasma treatment on both the inside and the exterior sides of those fibres, which means we can modify the surfaces and covalently attach biomolecules of our choice. And so doing this series of interesting steps, making the fibres, doing this plasma treatment, and then using stem cells, it turns out that we're able to develop a pretty unique technology. And the particular application that we're looking at, so there's a bunch of things that you could do, but we were really interested in the best fit of what our particular capability was to a real problem. So in a sense, people say about the laser that it was a solution in search of a problem. The laser, of course, turned out to be the solution to lots and lots of problems. But we were trying to find out what is the problem to which our very flexible, what I'm going to now call bioscaffolds rather than optical fibres, what is the best fit for that? And the one that we came up with was a nerve conduit. So when a nerve gets damaged, normally through a traumatic injury, such as a car accident or an explosion or being shot or those sorts of things, you can get really severe damages to nerves, which requires some sort of surgical intervention to resolve it. If the gap of damaged material is small, then you can hope that the nerve will join it up itself. But if the gap is more than 2 or 3 centimeters, you have to have some sort of scaffold or conduit to join up those 2 parts of the nerve. So the state of the art prior to the kind of nerve conduits that I'm talking about was to actually have another operation, extract another bit of nerve from somewhere else in the body and sort of sew it in. like a little patch from elsewhere in the body. But that turns out to have quite a lot of problems. It means that you have to have 2 surgeries. It can damage the nerve, obviously, in the place where it's taken. And often they don't match the environment properly. So our solution is to, and we're not the only people that are doing this, but we're the only people that are using this particular materials and processing technique, is to use this nerve conduit. And the nerve conduit is this soft, hollow tube, which is filled with the surface of the capillary is treated with has the plasma treatment. It has the biochemical environment to encourage the growth of nerves. And the idea, and obviously we haven't actually tried this in a person, but we're trying it in a lab environment. We're able to use these nerves. Sorry, my phone is going a bit bonkers. I don't know why. We've tested in an in vivo situation that we can grow nerves inside our fibres. And in fact, by tailoring the biochemical environment carefully, we are able to grow on the same nerve conduit different types of cells. So nerve cells, but also the sort of support cells that you would need for nerves. So we think this work is very exciting and certainly an unusual application of the optical fibre technology. So some of the, you can see on the slide here, we've got a little schematic of what we've done so far. So we take the fibres, which Simon mentioned, we do this internal and external plasma treatment. We convalently attach growth factors and the extracellular matrix. We then add these stem cells, and the stem cells differentiate, depending on what the biochemical environment is, into these neurons or these support cells. And we've also tried this with a number of other different systems, not just for neural systems, but potentially for making artificial bone structures as well. So the advantages of this, and I think it's worth saying that that 2 aspects of this very unique processes that were developed at Sydney University. So one is that fibre draw process for very soft, flexible fibres. The other is the plasma processing done through Marcella Billick's group. The combination of those 2 is pretty unique. We're also then working with our colleagues in the Faculty of Medicine on the stem cells. But the solution that we've come up with allows us to avoid the issues of rejection or the need for surgery to harvest replacement tissue. And it's a very versatile process. The next step that we're looking at now is to actually use the fibres to assemble more complex bundle structures with different types of cells in them. And so what we're actually looking to do there is to make some artificial bone type structures. So I think this is probably a real example of where research can take you in unusual directions. So some of the interesting things about research is that you can sometimes find things serendipitously, or you can explore these little rabbit holes that can take you into a different world. And I think I started off in this area working in photonics, and I've ended up working in stem cells. So that's pretty amazing. Anyway, on that note, I might hand you back to Martijn.
Thanks, Maryanne. I will share my screen again. All right, so one of our colleagues, Sergio Leon Saval, you can see a picture of him here, has laryngitis. He hastens to say he doesn't have COVID-19. He has laryngitis. He can't even squeak, he tells me. So I'm just talking very briefly about his work, and if you have questions about it, I recommend that you get in touch with him directly. His email is down the bottom of this slide. But so what Sergio generally does with his colleague Julia Bryant is astronomical instrumentation, or at least that's where it all started. They have a number of capabilities that you can see there. But what I wanted to concentrate on is some of the projects that they are working on and have been working on. So one of them is developing payloads for CubeSats. You may know they're very small satellites, so the payload has to be even smaller. Glint is a photonic nuller that is used in hunting planets. As by definition, a planet is very close to a star, and in order to see the planet, you somehow need to suppress the light from the star, and that's what a nuller does. Gnosis is a suppression unit for the near infrared, and that is for astronomy. Oops, what's that? That is for astronomy. That Chaitanya, can you kind of stop that, please? Thank you. Just let me just get rid of that. There, good. So if you do astronomy in between 1 and 2 microns, the atmosphere lights up like a Christmas tree, and that is because of OH emissions. And so Gnosis is a device that filters out those fairly narrow spectral lines so that you can look through the atmosphere to what is out there. And then Tiger and Sami and Hector are spectrographs. The work that Sergio and his colleagues are doing started in astronomy, and that's very clear. But it has taken them to other areas as well. They're involved in robotics, and the philosophy behind their research is that as astronomical observatories get larger, the instruments associated with get larger too, and at some point that becomes unsustainable. So they have started using technologies that have been developed for telecommunication. And as a human race, we have invested vast amounts of money. It's consistent with what Simon was just saying a minute ago, into telecommunications. And many of these devices can be used, or devices like it can be used for other applications, for example, in astronomy. And so Sergio and his students often spend time at astronomical observatories, and I remember this photo of one of his now former students sitting with her winter coat and woolly hat somewhere in a telescope, which of course invariably is at the top of a mountain, so it's pretty chilly, but it's very interesting and exciting work. And perhaps the last thing I wanted to say here is that although this work started out by borrowing technologies that have been developed for telecom, some of the technology that Sergio and his colleagues have developed are finding their ways back into telecommunications. So it is truly a two-way street. Okay, that's all I wanted to say about this. Let me go to the next slide, which is about my own work. And my own work, or the work I wanted to talk about here, is nonlinear optics. And before going into about the type of work I do, let me just talk for a few minutes about what nonlinear optics is. And in order to understand what nonlinear optics is, let us just remind ourselves what linear optics or linear physics is. Now, linear physics is, very broadly speaking, where superposition holds. In other words, if you have one solution and you have a second solution, then the sum of them is also a solution and is also allowed. Now, the problem with or a problem with linear optics is, and I'm exaggerating here somewhat, is that for that reason, it is somewhat predictable. And let me remind you that a math example here. When you do applied math, when you look at second order differential equations, if you have two solutions that are independent, an arbitrary solution is an arbitrary superposition of these two. So this really illustrates my earlier point that there is a certain predictability and there's not a lot of room for surprise, because if you have two solutions, that's all there is. Now, nonlinear optics is kind of everything else. It's everything where superposition doesn't hold. It's therefore more complicated, but I would claim in many senses, though not all senses, of course, it's also more interesting because there is room for surprise in a sense that is lacking in linear physics or linear optics. Now, I should say that much of physics, in fact, is nonlinear at some level, but you often you assume it is linear because it simplifies the treatment. But of course, the price to pay for it is that it limits its applicability. So why am I then interested in nonlinear optics? Well, rather than saying it is more complicated, I embrace it because the physics is very rich and there are some interesting applications, which I will talk about in the next few slides. So here are just some examples of things that people have done using nonlinear optics. And these are kind of covers from the journal Nature Photonics. So let me just go through them. They're not associated with us except for the one on the right-hand side, which I will get to in a minute, but there's frequency combs. So one of the things nonlinear optics can do is it can generate new frequencies for you. When you have linear optics and you put in a certain frequency, the system responds linearly. These frequencies can be suppressed or it can become larger, but you can never generate new frequencies. In order to do that, you need a nonlinear process. And the figure on the left illustrates a whole rainbow of colors. It's called a frequency cone. That generates a very wide range of frequencies. Then the second one on the left is an optical logic gate, which happens to be based on organic polyurethane, but that is not really the issue here for me. It's about logic gates, namely optical switches. And again, that is a nonlinear process. A switch could never be made using linear optics or linear physics. Then the third one is a modulator based on graphene. And a modulator is a device that allows you to modulate the throughput of a waveguide or a fiber. So this kind of pinkish thing is a waveguide or a fiber. And by putting this device on top of it and manipulating the device, you can manipulate the transmission coefficient. And this is therefore a way to put information on a light beam. And this is an extremely compact device. And again, this modulation function is an example of a nonlinear effect. And then the figure on the right, which is our recent work, which I will talk about now, is about solitons that, as you can see, are breaking the glass ceiling. And what I mean by that, I will talk about in the next slide. Okay, so when you talk about nonlinear optics, how do you even start? What is the basic theory that this is based on? Now, many of you will remember the kind of the fundamental relation in linear electromagnetism and optics, namely that the polarization P is proportional to the applied electric field E. And the mental picture I have there is that you have some atom and you apply an electric field, and the nucleus, which is positively charged, is pulled one way, and the electrons, which are negatively charged, are pulled the other way. And so they're pulled away from each other, and that forms a dipole. And the P is the sum of all these dipoles, the big P. That's essentially the physics. Now, if you pull very hard, sorry, one other thing. This is a bit like Hooke's law, right? You apply a force and things move away from each other. And so this relation P is epsilon naught chi E is the kind of atomic equivalent of Hooke's law. Now, as you know from Hooke's law, if you pull a spring too hard, you get deviations from Hooke's law. And the same is true for electrons bound to an atom. And this relation epsilon naught chi E that you know can then be considered to be the first term in a Taylor series. And there's a chi2 term that is quadratic in the electric field and a chi3 term that is cubic in the electric field. Now, for many materials, the chi2 term vanishes identically because of symmetry, including for glass that we're working on. And so the lowest nonlinear term that you get is this chi3 term that is proportional to the electric field cubed. And that term does a lot of interesting things. And one of which is that one of the consequences is that the refractive index of a material depends on the intensity I. So you may think that the refractive index is some kind of number, which may depend on frequency, but in fact, it in a subtle way depends on the intensity as well. And indeed, and in fact, if you look now at the window glass in the room you're in, then the refractive index of that glass is slightly higher now than it's going to be tonight when it's dark. Now, that effect is very subtle. It probably sits somewhere in the 10th decimal place. But if you do your experiment carefully, then you can make these effects visible and they can work for you. Now, what are the type of things we do with that? Well, we're interested currently in solitons. And let me very briefly explain to you what they are and why they're interesting. So this nonlinearity, where the refractive index depends on intensity, when a pulse propagates through a medium that is nonlinear, the pulse in time gets ripped apart. The spectrum of the pulse broadens and eventually the pulse just collapses. In addition to that, when you have dispersion, which is the effect by which the refractive index depends on frequency. And it also rips a pulse apart. And for example, you can see that in this case quite easily. If n depends on frequency, then red light goes faster or slower than blue light, depending on the sign of the dispersion. And so a pulse, which is a superposition of frequencies, the red frequency go ahead and the blue pulses frequencies stay behind, and so the pulse broadens. And that's what I mean by rips it apart. Now, the thing about solitons is that if you have a medium with both nonlinearity and dispersion, those two effects can balance each other. And you get a pulse that stays together in one piece, and that's what you call a soliton. So both ingredients themselves have the capability to rip this pulse apart, but if they act simultaneously with the right sign, then they can balance each other. And one of the analogies there that has been used is these runners on a mattress, and you can see that the runner who is going fast has to go uphill, and the runner that is a little bit behind can run downhill, and therefore, even though they want to run at different speeds, they stay together because they're on this kind of mattress. Now, of course, this is an artist's impression, but it actually captures at least some of the physics of these solitons. Okay, now, who are we then? Well, this is not the A team, but this is the S team, S for soliton. So we're meeting over Zoom as we're meeting now. So there's Joshua, who is the whiz in the lab. He's finished his engineering degree last year and is now working with us. There's me, the theorist, Tristan, Alexander, my colleague, also a theorist. Long is an honor student. He has a complete face, even though you see only half of it. And Antoine is a colleague of ours, also an experimentalist. And then we have two colleagues in the US who weren't on this call. It's Andrea Blanco Redondo and Darren. So now I've introduced you to the S team. The next slide gives you the S lab. So this is the experimental setup. The laser is, in fact, it's a fiber. We generate it in a fiber laser, and that is all on this optical table here. There's pump lasers here. There's apparatus that interrogate the pulses. And the secret of our experiment is this box here, which I will talk about in a minute. So the type of thing that started our interest is in what are called pure quartic solitons. And what they are is quite technical, but in effect, what it corresponds to is that it is a funny response of this mattress here. And if you want a full analogy, then the mattress would be less squashy, but would be steeper here at the edges than as indicated here. Now you can show that even though the mattress responds slightly differently, you still get these solitons. And these are the solitons fully measured using the setup that I showed on the previous page. And you may say, well, they look like a pulse to me, right? Sorry, this is as a function of wavelength, and this here is as a function of time. And you may say, gee, that looks like any other pulse to me. But these pulses have unique properties, and that is that the peak power is inversely proportional to the fourth power of the pulse length. So the pulse gets twice as short, the peak power goes up by a factor 16. And that is very interesting and very important, because these types of lasers are used for material processing. And an example there is this refractive surgery called LASIK, where they put these lasers on your eye and sculpt the cornea so that you don't need specs. What these processes rely on is ablation. So it's not that you heat your eye up, because that wouldn't be very good for it. You want to ablate material, and for that you need very short pulses. As you can see, these here are picoseconds. Ideally, you have them slightly shorter, hundreds of femtoseconds, and the peak power just takes some material off the cornea without heating it up. So one of the things that we're looking at is increasing the power of these pulses, making them shorter so that they can be used for material processing. So that is perhaps the application side of this work. The other aspect of this work, and this is my last slide, is its interesting physics, because the setup that we have, we can in effect dial in any kind of dispersion you want. So traditionally, dispersion has been seen as the property of a particular waveguide or a particular medium. We now have a laser where you can dial up any arbitrary dispersion. And so we're playing with that. And so what you see here, the purple, the orange curve here shows on the vertical axis, it is basically the propagation constant of the wave, and on the horizontal axis, its frequency. This is in some funny frame, but the details of which don't really matter. And now you see that if you go down, then you find you evolve from a dispersion relation with a flat top to one with two peaks. And as it happens, these solitons latch on to the peaks of this dispersion relation. And you can see that in the blue curve underneath, particularly in C and D, which shows on the left-hand side that the power as a function of wavelength. And you can see that there's a peak in the power associated with each of those peaks in the dispersion relation, and each of these peaks is a soliton. Now that is illustrated in the middle column, which shows basically the light intensity as a function of time and as a function of wavelength. And it goes from a single bumped structure to a double peaked structure here, right? And so here it is lowest row, you can see the two solitons that are coincident in time, right? But they differ in wavelength by about 6 nanometers. And these are called soliton molecules because you basically build bound states of light. These molecules travel through the laser. And trust me, lasers are not subtle environments. These light pulses get bashed around inside, yet these pulses stay together. So this is a bound state, which is only possible because of the nonlinearity of these two light pulses. Now, if you now look in the time domain here in the right column, what you can see here is that these two light pulses, they travel together, they overlap in time, but they're coherent objects. And so for some times they add up in phase, but for other times they add up in antiphase and they interfere destructively. And so if you now look at the intensity as a function of time that you can see here in the right column, you see this interference pattern. And so this is spectral interference between two different pulses that travel together. And again, for some times they interfere constructively, and for other times they interfere destructively, and that gives you this interference pattern. Now we're having a lot of fun with these pulses, and we're really the first ones and the only ones at the moment in the world who can build these very elaborate soliton molecules. We have made them more complicated and more interesting and richer than this. This might be like an hydrogen atom in which the two atoms are identical. We have also made, say, nitrous oxide in which the two atoms are different. So the low frequency soliton and the high frequency soliton are different species, and they also are bound together. So the type of work that we do has really two aspects. It has the applications in terms of high energy laser pulses for applications such as corneal sculpture, surgery, and we have this physics aspect where we can really generate these very elaborate bound states of different light pulses that stay together and propagate together. All right, that's all I wanted to say. I'll stop sharing. And oh, sorry, I have one other slide. I'm sorry. Sorry, let me just go back for a minute. So I have a number of other projects. A couple of nanoplasmodics, and Stefano Palomba and Alessandro Tunis will talk about that on Wednesday. I'm involved in the Starshot program with Boris Kulmi. He talked about that a couple of days ago. And I'm in a project associated with atmospheric water capture, capturing water from the atmosphere for drinking. But I just don't have time to talk about that. But I'm happy to talk about it offline if you wish. And that truly is it. Thanks very much for your attention, guys.
Thank you very much, Martijn, Simon, and Maryanne for this, for sharing your research. I think that it's very fascinating. And now I want to encourage students to ask questions if you have. So you can either unmute microphone directly and start talking, or send your question in the chat session.
Hello.
Hello. Yes.
Oh, I question for Maryanne with the fibers. That sounds very, very fascinating, but I'm still a bit confused as to how that works. How does the fiber then relate to doing that? Say, actually developing it for a person.
Yeah. So it's basically the fiber provides a scaffold onto which you can attach the biomolecules and onto which cells can grow. So ultimately, there's an interesting materials question that we need to resolve. Polyurethane is a biocompatible material, which means that it can stay in the body without causing inflammation and problems, but it doesn't, ultimately we want that scaffold to disintegrate in this particular application actually. So it's just providing a framework to hold and create the right environment for the cells to grow in the right way. So we know that when you take stem cells and you use them to grow different types of other cells, you need to create the right physical and chemical environment. And so in order to do that, you need to have something to create that right physical and biochemical environment. And that's basically what the fibres are doing. In one of the next stages of our research, we're looking to make the fibre not only biocompatible, but actually biodegradable, which means that over a period which ideally would be a few months, that fibre structure would degrade and effectively dissolve, like not actually dissolve, but you can think of it that way, so that you're just left with the cells that are then held in the right configuration by themselves. Does that answer your question?
Yeah, that covers it very well. Thank you.
Great. Thanks, Matt.
Okay, do we have any other questions, please?
I have another one if no one else is.
Yeah, go ahead, please.
So for Martijn, you mentioned trying to harvest water out of the atmosphere. Can you talk about that one now, or?
Yeah, I'm happy to talk about it. Let me just briefly do that. So, in order to condense water onto a surface, the surface needs to be cool. So there are a number of techniques to capture water from the atmosphere, and they're in essence large air conditioning units that cool a surface. The water condenses on it and it works, but the amount of energy you need is absolutely massive. I mean, these take as much energy as 50 houses or something like that. And so people, including ourselves, have looked at other solutions. So there are very nice solutions out there. For example, you use a hygroscopic material and then you heat the material and that releases the water. But what we're have been working on, and this is in collaboration with my colleague Kira Nato in chemistry and others throughout the university, is a method that doesn't require any energy input at all. And the idea there is that it has been shown the last 5-6 years that surfaces, if treated correctly, can passively cool below the ambient. And it sounds like it violates some laws of physics, but in fact it doesn't. And the idea is in essence the following. You make sure that these materials reflect sunlight, which means that they don't see the sun and don't heat up in the sun. Now, in addition to this, you have this material emits very strongly around 10 microns. And the 10 microns is important because the atmosphere is transparent at 10 microns. So if your eyes were sensitive to 10 micron radiation, you would look straight through the atmosphere and you would see deep space. Now, deep space, as you may know, has a temperature of 3 Kelvin. And so a structure that emits thermal radiation strongly at 10 microns sees deep space and radiates like crazy. And in fact, that process allows the passive cooling, and you can get probably about people have shown, and we included us, we have shown about 100 watt per square meter passive cooling. get that totally for free. This is one of the few cases that the lunch is truly free. So there's a lot of people looking at passive cooling, but the application that we're looking at is to then cool a surface and use that to collect water from the atmosphere. If you cool it, if you're capable of cooling below the dew point, the water will start to collect. And so it's a combination of physics, namely the electromagnetism of these surfaces, and chemistry, because you want the water that you collect to form droplets. Because if you form a film, as happens, for example, on your bathroom mirror when you take a shower, then it's self-terminating. So if the surface is covered by a film of water, it stops collecting more. So you want to form droplets which then roll off, and you can collect in a bucket. Now, we estimate you can collect probably 1 or 2 liters per square meter per day. So if you have a large enough surface, that is really worthwhile. And we're talking to people interested in this, for example, for application for off-grid water supplies and things like that. Okay, let me just stop here. I can talk about this forever, but I won't.
Do you have any other questions? Well, maybe I'll use my powers and ask Martijn the question about solitons, which is very fascinating indeed. But can you have a very simple explanation why they hold together? What is behind the stability of these solitonic lumps, or
would be a soliton in itself, or the soliton?
Well, yes, but can you explain what? Yes, it's soliton, or even the atoms.
So let me explain how the atoms stay together. So when you have a pulse propagate, so remember and I'll try to do this with my hands, which is difficult. But remember, the refractive index depends on frequency, on intensity. I'm sorry. Now, what does that mean? Well, so the peak of the pulse goes slower because it has a higher intensity than the front and the back of the pulse. So then you can ask the question, if the peak goes slow and the front and the back go fast, what's the consequence of that? Now, one way of thinking about this, and here I'll use my hands. If the front goes slow, the peak goes slow and the front goes fast, then the space between them is stretched out, right? And what happens there is that indeed the waves there get stretched and the wavelength becomes slightly longer. And so you generate new frequencies on the leading edge of the pulse, which are with a slightly lower frequencies than original. Now remember, one of the things nonlinear objects can do, it can generate new frequencies. And it does so on the leading edge, where these slightly lower frequencies get generated. And similarly, on the trailing edge of the pulse, you get a compression. Because again, the peak goes slow, the trailing edge goes fast, so they're pushed together, and you get blue frequencies. And so you get red frequencies on the front and blue frequencies on the back. Now you combine that with dispersion. And remember, dispersion means that different frequencies travel at different speeds. So if your dispersion now is such that red frequencies go slow and blue frequencies fast, then the red frequencies generated on the front are pushed back in, and the blue frequencies at the back are pushed back in as well. And you get this kind of churning motion, or that's my simple-minded mental picture, of these frequencies that are continuously generated, new frequencies generated on the edges, and then are pushed in by the dispersion. And that allows this pulse to stay together. Now, when you have this molecule, you can show that the energy of the molecule is less than the energy of the two individual solitons. And so there's an energy barrier to be that you have to go over in order to separate them. But that's the physics at a very simple level.
Thank you. All right, do we have more questions to our speakers today?
I have a question for Simon, if I may. So Simon, how flexible are these fibers that you were talking about? Can you squeeze them with your hands?
Yes. I should have brought a prop. You can stretch them with a band.
Okay. So that is what allows you to measure a heartbeat.
Yeah, at the moment we're using essentially just capillary guidance. As Maryanne mentioned, and I failed to mention, polyurethane is an awful optical material. Yeah. It doesn't guide light terribly well. But that doesn't matter if you're only measuring on the scale of the body. You know, if you wanted to build a transoceanic link, you really wouldn't do it with polyurethane. But from getting one arm to the other, it's fine. But instead of using a core cladding structure, at the moment, we're just using the most simple, it's technically an anti-guide, but just a hollow capillary. Nice. It has some benefits because it's intrinsically lossy. So the smallest perturbations to the structure cause a significant loss of light. And that's fine for what we're doing at the moment. I think it's one of the areas for further research is to explore proper anti-resonant wave guiding structures where we have good wave guiding intrinsically in an air core and then can frustrate that by even smaller perturbations.
Is that why one of your slides had this red looking fiber? Is that the losses from the fiber? I think
yes, there's two things going on there. The one worn on I think it was Alessio's chest, or was it Antoine's? I can't remember. Is one end of that fiber was glowing red, and that's primarily due to just the poor launch. You know, we basically butted the fiber up against a laser diode and held it in place with a bit of masking tape, so it was a really lousy launch. But where the fiber glows red down its length, that's because it's just not a very good waveguide. Yeah. So light's leaking out. That would be a disaster for a telecommunications application, but for our application, it really doesn't matter. As long as you get a decent enough signal at the end. Yeah. Then if you were to think about perhaps putting a hospital bed sheet with some of this fiber in to be able to detect what's going on with the bedridden patient, to detect their heartbeat, their respiration, and how frequently they move. Yeah. You need to be able to go probably tens of meters rather than half a meter, and that would require having a lower loss fiber. At the moment, we couldn't really aspire to do that, but for instance, the anti-resonance structures, which have been really taking off over the last couple of years for potential telecommunications applications, if we could make those in polyurethane, it opens up a whole new area of research. That'd be really cool. Drawing these really soft materials is difficult enough for just very small capillaries. Drawing things with features which are on the scale of the wavelength, which is what you need to do for the anti-resonance structures, is really quite difficult. So there's experiment and theory there that would open this up.
Okay, good.
All right, I think I don't see many other questions. Let me check chat. No, nothing is there. I think then it's time to wrap up our session, and thank you very much, everyone.
Thank you, Archil.
Thank you. Bye.
Cheers.
Bye.